All right, this is lecture 17 for ECE402. This is the first time I've done a lecture without an audience, so we'll see how this goes. Since there are no questions in real time, if you could email me today, then I can try to include answers to your questions in the next lecture. Also, if you want to give me feedback, if I'm talking too fast or if something else is wrong, or if you can't read the screen, just let me know, and I will try to improve it as I do more of these. So today we're doing lecture 17. We're continuing on fixed waveform synthesis. We started a little bit last time with variable duty cycle pulses and how you would make them band limited and that sort of thing. So now, this lecture, I want to talk a lot about a sawtooth. In particular, I'm going to come up with two words for sawtooths. Sawtooths? I don't know. One of those. One I'm going to call an engineer's true sawtooth. And we'll talk about that for quite a while. And then the second thing I want to talk about is what I'm just going to call a musician's sawtooth. Both of these are just words I made up, but they're ways to describe just ideas I want to talk about today. So, yes. So I'm going to talk through this sheet that you should have. You should have the PDF in front of you, but just like I would do if we had a normal lecture, I'm going to talk you through it. I have written some extra things on this sheet, which you can see here, and I'll try to explain more. So this first thing at the top here is what I would call, what I'm calling an engineer's true sawtooth. This is a digital sawtooth, right? We're talking about digital stuff. Much of the reason we want to do fixed waveform synthesis is because we want to implement algorithms that were originally done in analog, subtractive synthesis algorithms, and we want to do them in digital now. So if you want to do a sawtooth, this is what a sawtooth might look like. If you look at this closely here, that you'll see some odd things about this sawtooth, especially on your sheet, if you can't see it on the video so much. It's somewhat wiggly. And then there's this vertical drop for the sawtooth, but of course it's not a perfect vertical drop. There's some more wiggles here, and oh, look at this. This period here has higher amplitude than the previous period. Now, what's really important is what I wrote across the top there. After the digital analog conversion, this is a perfectly repeating waveform in analog. This waveform, when you listen, when you after the converter, you're going to have a perfectly repeating waveform. Every period will be identical in the analog continuous time world. In the digital world, this engineer's true digital sawtooth is different every period. And it has to be different every period if it's going to be exactly the same every period in analog. So think about that a bit. Stop the video and think about it if you need to, since you can't ask any questions. Normally we have a discussion in class at this point. But every period, it looks different. And if you look at this closely, the differences are actually kind of striking. Again, here on the negative end, look how different each period is. That's always going to happen. So in digital, even though in analog the world is the waveform is exactly repeating, in digital it is not. You do not have the same samples every period. So what makes this a perfect engineer's digital sawtooth? Well, first of all, it has a perfect saw spectrum. It has a sawtooth spectrum where the amplitudes of each partial are 1 over the partial number. So a sub n, or amplitude of the nth partial, is 1 over n. And that's all the way up to sample rate over 2. Okay, so it's band limited. It only has energy up to sample rate over 2. Right? The half sample rate is the limit, and that's super, super important because a digital signal can only have energy up to the half sample rate. If you had sharp corners in here instead of these wiggles, if it weren't band limited, right, a sharp corner takes infinite frequencies to represent. So if you had a sharp corner in a digital sawtooth, sure, you can make a digital sawtooth that has sharp corners, but if you convert it to analog, you're not getting a sawtooth. You're getting a mess. right? An aliased mess. It has to be band limited. And so that's why I call this a perfect engineer sawtooth. One that looks like a sawtooth in digital is not a perfect engineer sawtooth. It's just garbage. It's, for instance, if you think of the phase oscillator, remember in the phase oscillator, there's that integrator in there that integrates the phase. It keeps adding in your frequency value into your phase register. You can go review that again if you've forgotten about that. But when you look at what comes out of that, that's a sawtooth that goes up without wiggles in it, and then has a sharp drop, and then goes up again. And but if you can't play that through the D-to-A converter directly, it'll be an aliased mess. It's not what it looks like, and if you think it's going to sound like a good sawtooth, because you're imagining it's representing frequencies above the half sample rate, but you know that's impossible. So here you have all these little wiggles. Well, that's because it's band limited. And in fact, how the samples line up, how your sampling rate lines up with the period of the sawtooth, that's what determines what each period looks like. And the sample rate's going to, the sampling interval is going to line up differently with each period, and that's why each period you have a different waveform. That'll become a little clearer later in this lecture. There are a few other things I wanted to say about the perfect engineer sawtooth. One of them is, yes, as you know, the amplitude of each harmonic is 1 over n. Now, sometimes people talk about a linear spectrum for the sawtooth, and that when I was a student, that sort of confused me, because hey, amplitudes are 1 over n. It's not linear, it's 1 over n spectrum. But if you draw it this way, this is a nice picture I found on the internet. I hope I gave credit to it somewhere on this page. I hope so. Oh, yep, over here. So this has, this is the spectrum, but if you draw the spectrum on the horizontal axis in octaves or note numbers, so you see here, this is constant size octaves in the horizontal axis. And you do decibels in the vertical. Then 1 over n for amplitudes, like if A is 1/2, 1/3, 1/4, 1/5, if you draw it on these axes, then you get that straight line, or a 6 dB per octave slope. Now, as you know from previous papers we've read and stuff, normally if you draw spectra for musical sounds, you use linear hertz and linear amplitude. So these are weird units to use for that, but hey, if you used octaves on the horizontal axis or log frequency and decibels or log amplitude on the vertical axis, you would get this. So I want to talk some more about how you would get a sawtooth. We had talked about this in an early lecture. One of the ideas was, hey, if you're doing wavetables, you just have 512 different wavetables. Like the example I gave from how symbolic sound, or one of the methods that symbolic sounds use for doing it, you have 512 different wavetables. The first one just has 1 harmonic in it, or it's a sine wave. The second one has 2. The third wavetable has 3, all the way up to 512 partials. And if you have 512 different wavetables, well, then you pick the one that has the right number of harmonics to be band limited for whatever pitch you're playing at. Remember that if you play a higher pitch, you have fewer harmonics that you could possibly represent before the half sample rate, right? So if you play high pitches, you want fewer harmonics, but if you play very low pitches, you want lots of harmonics. Well, if you have this whole family of wavetables, then you can choose the wavetable that's appropriate, that has the right number of harmonics in it, and play it that way. There's other things you can do here, though. I want to talk about band-limited impulse trains, and then you can integrate those. So the first thing I want to say here, this is a band-limited impulse train. And again, hey, if you convert this to analog, this impulse train is a uniform height impulse train, right? It's as impulsy as you can make it. I mean, it's band limited, so you can't have anything above the half sample rate, but every one of these pulses will be the same amplitude in analog once you convert. They don't look the same amplitude in digital. So why in the world is that? I mean, that does seem confusing, or maybe it does. You know this actually from ECE402. It's not surprising, but you know, a lot of times you don't. prove lots of theorems and you do lots of algebra and lots of z-transforms, but it's not obvious that this should be true. But yes, if you have an impulse train in digital and it's going to be the same amplitudes, constant amplitude impulses in analog, well, it better be different amplitudes in digital. Again, it has to do with how the sample rate of the digital stream lines up with your impulse. Over here on your sheet, you have a band-limited impulse, okay? And here you've got, it goes up to 1. And then if you look at integer values along the axis here, it's 0 everywhere else at every integer value. It's 0 at 1 sample away, it's 0 at 2 samples away, 3 samples away, 4 samples away. From the center, it's always 0 if you're an integer number of samples away. So, if you had an impulse that just happened to be exactly at the same instant as the sample time, you would actually see a 1 and then all these zeros here. If the impulse occurred exactly synchronous with the sample, but that's never going to happen. That's sort of a toy example. What really happens is that when you have an impulse, it occurs sometime between two, it's centered, or its peak here is somewhere between 2 samples in your sample file, right? So if your impulse occurs, say, just before the sample in your sample file, then your samples, instead of being at integer values here, it might be 0.1 over it. It might be at 0.1, so your peak amplitude is going to be this, and then the next one is going to be a little bit negative instead of 0 at 1.1. At sample 2.1, it's going to be down here. At 3.1, it's going to be there, and so on and so forth. And that's why over here you see different amplitudes each time through. It's because the impulse train, the frequency of the impulse train, or how often these pulses happen, that doesn't divide evenly into the sample rate. Right? It almost never would divide evenly into the sample rate. And so some of these impulses are better aligned with the samples in one period, and then the next period is more poorly aligned. This is better aligned, better aligned. And if they're, again, you can see from this over here, from this band-limited impulse graph, that depending on how it's aligned, you have different values. Again, this is a band-limited impulse. You know that ideally an impulse is all zeros and then a 1 in one place and all zeros, but that's not band-limited. You can't have this sudden 1. If you had that would require all frequencies, and you can only go up to the half sample rate. So if you're going to limit it to the half sample rate, this is what an impulse looks like, and here you're seeing in between the samples. So when you take this impulse and you make an impulse train, you're going to place these maybe 22.7643 samples apart. Well, because of that 22 point, everything after the point is going to get you different values out of this band-limited impulse each time. You're going to land different places on them wiggles. And that's why you end up with what you see over here. Now, if you study this picture, there are a few little things that are hard to tell. One of them is, yes, you have this impulse and it goes up and then it wiggles around. That's fine. Every period is slightly different. The peak is slightly different, and how it wiggles around is slightly different. One thing that's hard to see, that's very important to realize, is on this part here that looks like it's a 0, this doesn't go between 0 and this big positive value. This is actually all slightly negative. The average of this stuff in here is slightly negative. It's all slightly negative. If you take this impulse, you know this from your Fourier transform theories, if you integrate this band-limit impulse train, you're going to get a band-limit sawtooth. You're going to get a good sawtooth, band-limited sawtooth. Aside from math errors, it's going to be a good sawtooth. So if you were to integrate this, it would jump up, and then it's slowly sinking down just because the DC on these in-between parts is negative. And then it's going to jump up again. So yes, so you integrate this, and you will have your band-limited sawtooth. So if you can make a band-limited impulse train, say for instance you had a table that had all of these values in it, how would you make a band-limited impulse train? Well, you have this table here, and now your if you want an impulse at a certain point here, say at sample 100, let's say this is sample 99.5, or maybe it's 99.8. I'm not sure what it is here. But you look over here, say it's 99.8, so you take the samples at 0.8, 1.8, 2.8, 3.8 out of this table, and hey, you just copy it into here. Right? If it, depending on how it's lined up, you take the samples and copy them here. If this explanation makes no sense, please write me email. I can try to find a better way to explain it. But you have to take, this thing here is not going to exactly line up with the sample. This peak here will be slightly off of one of the samples in your sample file. If it's off by 0.2, you just add 0.2 to all the integer values here. So you have at 0.2, 1.2, 2.2, 3.2, 4.2, you index into this, and you have it here. Because it's an impulse train, you got to remember this sync thing here keeps wiggling on. So you have the effect of this impulse and this impulse and this impulse. These various impulses all have long tails on them. So if you have a series of impulses, you have to add up the effect, the data from this impulse that's centered here, but also the tiny little side wiggle that's still left over from this one and from this guy's sync here. You add all those up and you can make yourself an impulse train. Then you can integrate it and get a sawtooth. In practice, actually, I've tried to do these things, and in practice, it's been, I had very little luck with this. People write papers about it, people just say they do it, but when I actually tried to do it for the Eagan matrix, for use in the continuum, I could never get it to work because I had unstable DC offsets. And what am I talking about there? Well, when I do a table lookup to get these values, and then I add them up and I make these impulses, because when I'm integrating this thing, I just get too many small numeric errors. So I'm getting these changing DC offsets. The waveform doesn't stay, the sawtooth doesn't stay nice and centered around 0. Instead, it's like floating up and down. In fact, it's doing so quickly, I couldn't low pass filter out, this DC offset problems. I couldn't filter that out without affecting the waveform. So at least in my experience, others have had better experiences apparently, but in my experience, it's very hard to integrate these BLITs, these band-limited impulse trains. There is something, though, that did work very well for me that people have talked about, and that's this bipolar, a bipolar BLITs. So what is that? This is the same as this impulse train, except you have one that's negative. You can see here, there's a -1, there's -1. And then by 180 degrees phase, you have the positive version of it. And you just add those two together. So now you've got negative pulse, positive pulse, negative pulse, positive pulse. And it just turns out that numerically, I had a lot of luck integrating these. So again, I did it by table lookup to figure out the values to make this band-limited impulse train, and then I integrated it. And if you integrate a bipolar BLIT, you end up with a square wave, right? Because you get the -1, then you get this big positive one, -1. You integrate that, you get a square wave. You integrate that again, you get a triangle wave, and all of those are band-limited. So that's kind of a cool thing. So it is possible to get a square wave and a triangle wave this way. I had little luck, though, with a sawtooth, which is super, super important. It's like sort of a core thing. I wanted to integrate BLITs, band-limited impulse trains, to get a band-limited sawtooth, and had little luck with that. So I'll talk about what I do on the next page. Again, I say other people have been more successful with this. I'm just talking about my own experience. I never was able to get it to really work. So here we've got, instead of doing wavetables, instead of trying to build up band-limited impulse trains by doing table lookups and that sort of thing like we were doing in the previous page, and instead of doing like what the phase oscillator normally does, or what we started off saying, in the phase oscillator, I have it sort of drawn down here, in the phase oscillator, instead of putting a table lookup here, put a math function there. So you can have all the same setup, this thing that generates the phase, got 24 bits of accuracy. In the math function, you might as well feed in 24 bits. But this math function I'm showing here has two parameters, I'll talk about a little later, S and K. And so that's, this DSF stands for discrete summation formula. And yeah, so if you have the the processor to do it, you can do a discrete summation formula. So what is a discrete summation formula? Well, discrete summation formulas are based on this thing of sums of exponentials. So it's a special trick that works with exponentials. You've seen this, I think, on your PDF. I think I corrected this here. But you've seen this thing that the sum from k equals 1 to big K of r to the k has this nice form, right? And you've seen that in 310 and in other classes. So you have this sums of exponential thing is a super useful super useful thing, because now you can evaluate this sum, which, depending on k, where if k is the number of harmonics, this could be a very large k. You might need 500 harmonics, you're playing very low note, or you might only need 2 harmonics, you're playing very high note. In any case, if you evaluate something using this sum of exponential formula here, then it doesn't matter if you have 2 or 100 harmonics or that you need, or how big your k is. It always takes the same amount of time to evaluate. So what one thing you can do here with the sum of exponentials. Well, what if you want to do a band-limited impulse train? What is a band-limited impulse train? Well, it has all frequencies present. So it has cosine k theta for k equals 1 to big K, where big K is however many harmonics you have in the impulse before the half sample rate. Big K might be 100. So that means that up to the half sample rate, you've got 100 partials, 100 harmonics that you want to compute. This theta here in this formula, that can be in the phase oscillator from the phase register, from the integrator and the phase oscillator, that's fine. You've got cosine of k theta for k equals 1 to big K. So you can write that as a sum of exponentials. You need to write it as a sum of exponentials if you want to use this DSF trick. So what you do here is you write k equals 1 to big K of the real part of e to the j k theta. Right? You know this. The real part of this, is the cosine. Right? You know that from ECE402. So here you have a sum of exponentials. You can move this real on the outside and do some manipulation, and you end up with this formula here. So this formula here, nice closed form thing, doesn't have a sum in it anymore. Right, because you use this trick, you've owned this mathematical identity. So now you've got this formula here, which lets you compute a BLIT with any number of harmonics, big K. And say you want to play a higher note, well, you can make big K smaller. If you want to play a lower note, you can make big K bigger. So it's very easy to control in real time and keep it band limited by adjusting big K. You've heard this thing before because, it's what's used in the Eagan matrix. So I'm going to play you some examples of how this works in the Eagan matrix. On your sheet there, you can see more. I'm running out of space here on my phone camera. But what I did here is I have... this is what's actually evaluated in the Eagan matrix. Very similar to what's above. I take the imaginary part of either, so it's a sum of sines instead of a sum of cosines. So the impulse train doesn't look the same, but it'll sound the same. And now you've got also e to the minus k alpha. So there's exponentially decreasing amplitudes for each harmonic. So what can you control on this DSF? Well, you can say how fast do the harmonics change, because you don't always want just a bipolar band limit impulse train. boy, that's really raucous. It has a lot of harmonics that are all equal amplitude. You don't really want that all the time. Instead, you can get here, you can control alpha so that it's not just an impulse train anymore. You have this alpha control. You can say, you can specify how fast the harmonics die off, but only in an exponential way. If you want them to die off linearly, well, this has to be a sum of exponentials for you to use the DSF math identity. So yes, so this is decreasing harmonics of sine waves. And what I did then, because it just seemed nicer to control within the matrix, I actually made this parameter S. When S is really what people control, it just feels better to the musician. It has a nicer range of control. It's really equivalent to alpha. It's just scaled and offset. So here you've got the S parameter and big K, and that's what I had drawn over here. The S parameter is the spectral parameter that you know in the spectrum column, or the spectral control in the oscillators in the Eagan matrix, and then you've got the big K there. So the big K is just the number of harmonics. And you don't generally control that in the Eagan matrix directly. It knows what frequency you're playing at, and it just automatically gives you a big K that fills out all the harmonics up to the half sample rate. All right. So, what is going on here then? S is a musically useful timbre parameter that you can control. We use it in the range of 0 to 1, as you know. The DSF pictures that you have in this first column there are with yes. Oh, okay. I'm sorry. Yes. If you want a true band-limited impulse train, you can set S equals 1 or alpha equals 0. That means that here it's all same amplitude, e to the minus K0. So they're all the same amplitude sine waves. So you can do that. It's not quite a band-limited impulse train. It's the harmonic conjugate of a true BLIT, but it will sound the same. Yes. But you can use other values of S and get, as you have on your PDF there, you can get these different wave shapes. You can also integrate the thing and then get these wave shapes. Why would you integrate it? Well, because it sounds nice. One of the problems here is you have this exponentially decaying amplitudes of each harmonic. Once you integrate it, you know from your Fourier transform properties that this will be linearly decaying harmonic amplitudes, 1 over n's instead of exponentials. So you can get, well, something very close to a sawtooth. You can get the engineer sawtooth out of it, and yes, you can get the spectrum of an engineer sawtooth out of it. Because here I'm doing the harmonic conjugates, it won't look like a sawtooth. You'll see a shape that looks more like this. Well, I'm not going all the way up to 1, but you'll see a shape like this. And so it doesn't look like a sawtooth, but it has the same spectrum. It's a harmonic conjugate, sine swap for cosines. But other than that, it's the same as a sawtooth. It turns out that musicians, when they are want to hear a sawtooth, it varies. But often they don't really want a true engineer sawtooth. Early on, when the first sawtooth oscillators were made by for the Trautonium, and then later, of course, Bob Moog and the Moog synthesizers did, the sawtooths with just beautiful low-pass filters. Those sawtooths, if you actually look at them, are not perfect engineer sawtooths, not even in the analog domain. They don't look like a perfect sawtooth. They sound close to it, but they're creamier or they sound better in some way. And so often, and it's confusing to an engineer, but when a musician says sawtooth, they actually want something that is nearly, a similar spectrum, or reminiscent of what a true engineer sawtooth would be, but not exactly that. In fact, here, this thing here is not exactly the harmonic conjugate of a true sawtooth, but it's close. And it turns out this is actually what musicians generally prefer when they're using the Eagan matrix. I want to show you some examples of the Eagan matrix playing with time-varying control of S. So it's this formula here. It's just a digital summation formula instead of a wavetable. And it can be time-varying, of course, because you can vary S, as you know. And I just want to play you some examples because it sounds quite impressive. It's not something that you normally hear in digital, because very, very often in the digital world, you hear sounds that are far away from the half sample rate, because they just don't want to alias, and the algorithms end up often not going above the quarter sample rate or even lower. Where here, because we have this direct control of K, it's very easy really to have every harmonic right up to the half sample rate and nothing beyond. So it's strictly band limited all the way up to the half sample rate. So you get a much more analog-y sound. Just listen for like the clicks you get out of it and the just the range of sounds. So I'm going to go ahead and play this here. You can hear it through the phone, but you can also hear the sound example that was included with your PDF if you want to hear better quality. So this is called the clinical oscillator examples. The name clinical oscillators, I have to give full disclosure here. Clinical oscillator was not meant as a compliment. Ed Eagan, when I first came up with these DSF algorithms, was so proud of how they sounded so good. He sort of liked them, and I think they've grown on people now. Now they've actually really been featured in quite a few pieces of music. But at first he said, oh man, compared to my analog synths, this still sounds really antiseptic and clinical. So that's where the word clinical came from. All the same, please listen to it and see what you see if you can hear that aspect of things where you really have the high frequencies right up to the half sample rate. So none of that clicking you hear is aliasing. That's really just right up to the half sample rate. Changing S dynamically. So yeah, so in that example, you heard everything from really a band-limited impulse train and the total raucousness of that, all the way to almost sinusoidal, integrated and non-integrated clinical oscillator. So yeah, it's sort of interesting to hear just what the bare bones. This is no filters. This is just the DSF controlled oscillator that you have in the Eagan matrix that you've been using in lab. Okay, so I'm going to say here, though, when musicians want a sawtooth sound, they generally do not want the true engineer sawtooth. They prefer S equals 0.8. What I want to call the musician's sawtooth, just to distinguish it from being a perfect sawtooth shape with a perfect sawtooth spectrum. See, when I say engineer sawtooth, I want something that's not aliased. I mean, something that's aliased is just garbage, but something that has a perfect spectrum all the way up to the half sample rate, you know, that's a perfect engineer sawtooth. But often that's not really what people use. So various famous musicians have told me that that they really prefer this over the strict sawtooth. The continuum in the Eagan matrix does have an engineer sawtooth. It has a very, for instance, in the wave bank, if you use a sawtooth in there, those are strictly band limited, you know, engineer sawtooths, and they have that quite stark sound. In that case, because of the supersaw effect, it is actually very nice to have the real sawtooth. So let's talk about the supersaw just for a little bit. Early on, when digital synthesizers were a new thing, it was very easy to make an aliasing sawtooth, right? You just do the same thing the phase oscillator has in it. You just keep adding up a number, let it overflow. And if you do that, you get something that's sawtooth-like, but boy, it aliases. There's just so much garbage in it that it's unlistenable. So in the good tradition of, well, can you really make it band limited? That was really hard. So rather than trying to fix it and really make it a perfect engineer sawtooth, very smart engineers at Korg and elsewhere figured out to make the super saw. So what is that? Well, instead of just making one sawtooth, they're really inexpensive. One thing that really helped cover up all the grit, all the noise and dirt in the sound due to aliasing was to play a whole bunch of sawtooths, like 7 or 8 of them, slightly detuned from each other. So it makes for a nice full sound and it covers up a lot of the problems. So it's a very clever idea because now instead of having to say, you know, this sawtooth is pretty dirty and not so great. Well, you have a super saw, right? You put super right in its name. You get a whole bunch of sawtooths at once. It's a new sound that's actually still useful nowadays. It's a very, you know, it was a workaround, but it was a very smart thing to do and a very nice nice sound in its own right. So the idea is to cover up the aliasing. Actually, there are 2 main features there. One of them is you play a bunch of them slightly detuned from each other, so it sounds more interesting to your ear and covers up some of the problems with it. The other thing is you can do a high-pass filter on it, so that there's alias frequencies that are below the fundamental of the super saw. Well, you certainly don't want those, so you just filter those straight out. But for the aliased components that are above the fundamental, well, you can't really filter those out, and so you hide them using the supersaw effect. And that supersaw effect is still useful nowadays, and for other reasons sometimes people want a real sawtooth, real engineer sawtooth, I'd say, and that's great. But on the continuum, I think when people are using sawtooths, especially with those with the oscillators in there, so not the wave bank, but the oscillators, they generally don't use what was really a sawtooth. They do something that looks like this. Well, first of all, this is a harmonic conjugate of a sawtooth, right? So that's why it looks like this instead of the sawtooth shape. But it's quite sharp. It has, it comes to a point. It's band limited, and it looks like the harmonic conjugate should somewhat. If you're interested in harmonic conjugates, you can look that up in Wikipedia too. They have I believe they have the sawtooth example there, and but this isn't the exact perfect harmonic, the harmonic conjugate perfect sawtooth. In fact, here's a spectrum for it. So there's several things you'll see about the spectrum. Over here, it goes to 0 at the half sample rate. You can see this is at, this one here was done at 36 kilohertz, I think. It goes to 0. That big K parameter really works. But look at this slope here, right? This is a constant octaves here. So you would expect it to be 6 dB per octave, but it isn't. The fundamental is a little, here, and you see it's sort of 6 dB per octave, but then it drops off faster in higher frequencies. And that seems to be something that people like. So this is with S parameter 0.8 and integrated there in the Eagan matrix. They like this for an engineer sawtooth. Now, I've had the privilege of being compared by very good musicians to the very best in the world and the very most famous. The Moog Voyager sawtooth being one of the most famous and best loved sawtooth sounds in the world. And so people compare, like, well, what does the Eagan matrix do compared to what does the Voyager do? The Voyager being an analog synthesizer. It has some digital controls, but it's even the new Voyager is still generating the sound analog. And so what's going on here? Well, people actually say no. They actually prefer the Continuum's musician sawtooth if they're going to process a sawtooth. Like normally sawtooths are made for subtractive synthesis, right? You're going to filter it out. You're going to work with the sound some more to through a chain of filters and other effects to get the sound you want. And for that, they really like the one that I generate even better than the one out of the Voyager. But the one on the Voyager wins for if you just kind of play it as a solo. It still sounds better. So what is different about the Voyager one than the one that I'm generating? I'm already trying to generate a musician sawtooth. I put a lot of work into it, but I haven't. They're still yet better out there, at least for solo work. Well, look at this thing here. Now this is again the same kind of graph. It's not 6 dB per octave. Well, it is sort of close. It falls off faster at high frequencies. Of course, it has no half sample rate because it's analog. But there's a few differences here. One of them is the fundamental is actually more present, is stronger than you would expect, and stronger than it is on the Eagan matrix, on the Continuum's sawtooth. And then it kind of drops off here, but there's like this extra dip here. And what is that? Well, you get this nice creamy effect. You know, when they do movies and they have some beautiful woman's face, and of course a beautiful woman's face, at least traditionally in movies, is supposed to have no blemish on it. It's almost like an android's face. It's supposed to be totally perfect. So they take the picture through, I don't know what, through cotton or something, to make it so you can see no variations on their skin. And whether, I'm not sure what I think of it, but anyway, that's what's done. And it just takes off any edge and makes this, I guess, the skin look totally perfect. Well, the counterpart in audio, like if you have somebody's voice and it's a bit shrill or something, there's this trick that that's used to put to filter out just a little bit around 2,500, 3,500 hertz in this range here, and that just makes that voice just that much nicer. Gets rid of that shrill effect, makes it creamier. At least that's a word that I think I've heard musicians and sound designers use for that. It's if you just lower down those frequencies up there, you get this creaminess, and that creaminess is not present in what I'm doing. You could add it, you could play with it. It's a pretty subtle effect. People that are talking about these things are quite sensitive about it. But if you listen, you can hear that. So I'm going to play you some examples here, the first thing, I want to play you some Voyager examples. Here's something I got to show you though, just because because of math errors, I was getting too much math accumulated when I was trying to do the straight, the DSF for a sum of cosines, so I did a sum of sines, and I was getting, I avoided my math errors there. So I've been using the harmonic conjugate of a sawtooth. So this doesn't look like a sawtooth, it just sounds like a sawtooth because it's the harmonic conjugate of a sawtooth. Well, the Voyager, look at its sawtooth. It's even weirder. And, that's one of the great things about Bob Moog and why he is probably the most famous and most respected synthesizer builder ever. He has a good ear. He had a good ear. Unfortunately, he passed away a few years ago, but he had a good ear, and he was good at engineer, but in the end, it sounding good was paramount. And I'm sure that he messed with this thing, and he was listening to it. I mean, he knows darn well what a sawtooth should look like. He knows all these things, but if the time domain waveform looks a little funny, if it sounds right, that's good enough. He also had another issue here. This was a generator where you could choose between different wave shapes, sawtooth or triangle or sine, various others on the Voyager. So he also had a circuit that had to do more than the sawtooth. So that was another consideration in why it might look this way. But if you look at this thing, it's a pretty funny looking waveform, complete with this little glip here and whatnot. It sounds great. So as an engineer, if a student came in and handed and say, "Oh, here's my sawtooth generator, it looks like that," us academics would probably roll our eyes at it. But actually, it's a very, very good sound. I'm going to play you this Wayon example, or Wayoon, I don't know how to pronounce it. This is on the Moog Voyager. Actually, I have several of them here. I'm going to first play you this glass example. Again, this is continuum controlling a Voyager. So here we go. I should say a few things about this. These first two examples are just one Voyager patch, meaning it's, no knob twisting during these examples. This is just playing the Voyager with different finger technique on the continuum, but not setting up the Voyager synthesis chain any differently. And here we go. This first one is called Glass. Not sure how good the recording is that you're hearing or how good your earbuds are, but in any case, it has that nice analog-y feeling to it. You can definitely don't feel hemmed in by any sample rate there, something that the previous example was also trying to get in digital. But here's another one. This is called Wayoon. Again, one patch, just different playing styles with fingers on the continuum. Just beautiful sounds. Again, something that is often missing from the digital world. It just does. Okay, so here is one more example, again from the analog world. This is actually multiple Voyager patches, and then there's one Pianotech modeled piano with it. So you'll hear analog synth, you know, the Voyager, the Moog Voyager, and then Pianotech accompaniment. You'll hear things in here like a cello line. That cello line is pretty much just the Voyager Sawtooth, with just very little processing on it. And much of it, of course, is a musician's skill here to play cello idioms and that sort of thing. But various musicians have told me that have owned the Moog Voyager, and the Moog Voyager has been under constant development and constant production and improvement since the 1960s. And they tell me, you know, once they got the continuum to control it, wow, you know, this Voyager is making sounds I've never heard it made before. Even though it's the same synthesizer, the control is super, super important. And you'll hear that in some of these lines. I mean, all you're hearing in some of these is very simple filtering of a sawtooth. And still it sounds quite pretty. I hope. Come on. All right. Yeah. So all the examples so far that you've heard today, well, and the next one too, were all done by Edmund Eagan. But this next one, I want to do an sort of in juxtaposition to what you just heard. I mean, this beautiful, warm, full sound you just heard in this last piece. Then in this one here, oh, no. I have one more example first. I just love this. I love the analog sound too much. Again, here's the analog sound. The Voyager. This is called Days After September 23rd. So again, if you were able to hear that, I don't know how good the quality is, but if the sound quality was good, or if you heard the file separately from this presentation, yeah, that's something challenging doing digital, to get all that stuff without the aliasing noise and the grit of aliasing, but to get everything from clicks to very creamy sound to all these things that require energy right up to half sample rate in digital. Well, in the analog world, there is no half sample rate, so that isn't such a challenge there. But it's very hard to do the same sorts of things in digital. This next thing I'm going to show you, though, is something where we're really using a perfect engineer's sawtooth. It doesn't have that creaminess. It doesn't have that warmth of this musician sawtooth, but it's really appropriate in this case. Because in this case, this is from Ed Eagan wrote some music for a scene in 2001, A Space Odyssey, for the Jupiter mission segment. So he wrote this music, and it's engineer sawtooth with very simple filters on them, inspired by what could be done on the Trautonium of the 1920s. Just two bandpass filters on a very simple engineer sawtooth. And yes, it's very stark. It doesn't have that warmth, but in this case, it's very appropriate for the segment. I'm going to point my camera at my computer screen. You can also find this video elsewhere on YouTube. Yes, so you'll be able to see at least a little bit here. If you look at if you look closely, you'll be able to see reflections in Hal's eyes of Ed playing. But listen to the starkness of this, and a starkness that's very much appropriate, I think, for this particular piece of music. So yeah, what you were seeing there as well, you could see Hal's camera eye there, and Ed's playing in it. You could also see the circles on the surface that you're familiar with in the editor, the on-screen display of the surface. In the background, there was scrolling MIDI messages. I suppose a little bit like the 8080 instructions that were in the Terminator's view. I don't know. In any case, yeah. The starkness is quite pretty there. So yes, so the stark can be good, and again, there's an example of an engineer's sawtooth used in its full glory and its full starkness. Okay, well, we've gotten to this point of the lecture much faster than I normally do, but there's also nobody asking me questions. So please do send me email with questions. I only have a few more end comments to make here before we're done with this fixed waveform synthesis. There is always this idea that, oh man, in analog you could do all these things because you didn't have a half sample rate limitation, and we could really get some amazing sounds out of it. Well, there are some things to keep in mind. One of the things that happens in analog synths, especially if you're not controlling them from continuum or from a continuous control like that, much of your sounds traditionally were controlled by ADSRs. So what is that? We've talked about this before, but you have envelopes where you have the attack, the decay, the sustain, and the release. So for amplitude envelopes, the attack, normally the control you have over the attack is just how long does it take to get to peak value. Decay is how long does it take to get to sustain value. And sustain is what is the sustain level. And then release is how fast does it release. And also, is the release exponential or linear? But there's generally just 4 knobs and a switch for an ADSR envelope. And this is all you have. So some of the stuff you're hearing for analog, we're cheating a bit because you're controlling it through, what you were hearing there was controlled through a continuum. Historically, though, there have been ribbons. There's been various other ways to do continuous control. In general, keep in mind that if you are looking at acoustic sounds, their envelopes are much more complicated. This is a very useful structure. You can use it to control filters. You can use it to control just direct amplitudes and all sorts of things. But here is an example from heterodyne analysis, from a short window analysis done by Jim Beauchamp for a trumpet tone, right? And you look at, wow, there's a lot more than 4 segments there. In fact, each partial has a very different shape. Each harmonic has a very different shape. So there's a lot of data there. So in that way, it's important, I think, to keep in mind, at the time the analogs, now we're all looking back retro, but when they didn't have sampling, all these sounds that are sampled now for you, well, they have complicated spectra like this thing here. If you're generating all the spectra with just ADSR envelopes, it is quite limited what you can do. And I just wanted to put that juxtaposition of having one of these or all of these different envelopes for your sound. It's quite a difference. All right, so that was fixed waveform synthesis, and I threw an ADSR here because it's part of subtractive synthesis, as is fixed waveform is very important for that. I'm going to give you a homework assignment here, also a lab assignment, and you'll see that in your handout. I'm going to talk more about what this homework does in the next lecture. Also, I'll answer any questions you email to me from this lecture. This homework assignment is about multiple wavetable synthesis, musical instrument tones. We'll talk about some techniques like genetic searches and such, which might be of interest to you, for even non-musical applications. But this is a sort of an extension of fixed waveform synthesis and a few other things you can do with it that are quite different from the traditional subtractive synthesis. Thank you very much. I'll see you on Thursday.